Programming at compile time. In this section, we're going to take a look at compile time computations with Constexpr, manipulation of variadic template type lists, standard library features focused on metaprogramming. Let's begin with the first video, constant expressions. In this video, we're going to take a look at what constant expression means, the Constexpr keyword in C++ 11, 14, and 17, and finally, practical use cases of Constexpr functions. Let's begin with constant expressions. You might have noticed that values such as non-type template parameters or array sizes do not accept runtime values. As an example, if I have a struct called foo here, which takes a template parameter int I, and I attempt to initialize this struct, passing an int I that was initialized from standard input, you will get a compile time error. The error will tell you that I is not a constant expression and cannot be used in this context. This makes sense, as these values must be known at compile time. The C++ standard refers to expressions whose result can be computed at compile time as constant expressions. In this case, if I pass 5, which is a numeric literal, instead of something that I get standard input, the code will compile as 5 is a constant expression. Before C++ 11, only a few language elements were considered valid constant expressions. These include expressions consisting of arithmetic literals and enumerators, non-volatile const variables or static data members, non-type template parameters, and size of expressions. Since C++ 11, and especially in C++ 14, these limitations were greatly relaxed. If you're interested in seeing all the possible language elements that can be considered constant expressions nowadays, feel free to take a look at the CPP reference link below. Since C++ 11, users can now write functions that compute constant expressions, thanks to the new Constexpr keyword. In this code snippet, I'm defining a function called 5, marked as Constexpr, which returns an int, and the body of the function is really simple. It's just going to return 5. Thanks to the Constexpr keyword, I can use 5 in any place where I need a constant expression. As an example, in this std array initialization, I can use 5 to set the size of the array. Before C++ 11, it was not possible to use a function call as a constant expression. Usual tricks include using enum or templates that expose a static const member in order to compute complicated constant expressions. In C++ 11, Constexpr functions were limited to a single return statement. This limitation required developers to either use recursion or unnatural code in order to produce useful effects. Here's an example of a Constexpr function that calculates the nth Fibonacci number. The way it's implemented is by using a single return statement with a long expression composed of multiple ternary operators. If the passed input is 0, we will return 0. If the passed input is 1, we will return 1. Otherwise, we will recurse by summing the Fibonacci number that was previous to x and the Fibonacci number 2 times previous to x. If we check this out on Compiler Explorer, you'll see that we are able to use static assert to make sure that our Fibonacci function returns the correct values. This means that invocations of Fibonacci such as this one are constant expressions and can be evaluated and checked at compile time. Constexpr functions can be executed both at runtime and compile time. If all the arguments are known at compile time, the function might be evaluated at compile time. This is not guaranteed. If any of the arguments is only known at runtime, the function cannot be evaluated at compile time and will always require some runtime code to be executed. If the function is invoked in a context where a constant expression is required, such as the size of an array, compile time evaluation is mandatory. If the compiler is not able to evaluate that function at compile time, an error will be produced instead. Constexpr can also be applied to variables. It forces variables to be initialized with a constant expression. In this example, if we say Constexpr int n0 equals 42, everything is okay, because n0 is immediately initialized with a constant expression. If instead we say Constexpr int n1 without initializing it, we will get a compile time error. All Constexpr variables must be properly initialized. Now, imagine that we have a function called readInt from standard in. And this function simply calls stdcin and returns the integer that the user passed in the terminal. If we attempt to initialize a Constexpr int n2 with the return value of this function, we will get an error, as the function is not a constant expression. If we try to mark the function as Constexpr, we will get another error as stdsyn is not usable in a Constexpr context. Finally, this other example shows a function called triplicate that, given an int, will return 3 times that value. This function is marked as Constexpr. If we attempt to initialize a Constexpr int n3 with a function called to triplicate, everything will be fine, as the passed input argument here is 5, which is a constant expression, and triplicate itself is marked as Constexpr. After we do this, we can even use static assert to make sure that n3 is equal to 15 at compile time. That was an overview of Constexpr in C++11. Let's now move on to C++14. Since C++14, Constexpr function restrictions were greatly relaxed. Almost any language feature can be used inside the body of a Constexpr function, except dynamic allocation, runtime-based memory accesses and casts, such as reinterpret cast, expressions that would lead to undefined behavior, or function calls to non-Constexpr functions. The list continues with more restrictions, but the general rule of thumb is, if the action you're performing requires some kind of runtime-based address or some kind of allocation, then it will not be allowed in a Constexpr function. Otherwise, you should be good to go. Here's an example of a Fibonacci implementation in C++14 that does not use recursion and looks like a normal imperative Fibonacci function. As you can see, I'm creating local variables a and b to hold the previous 2 numbers of the Fibonacci calculation. I am then using a regular for loop in order to calculate the Fibonacci sequence. Inside the for loop, I'm mutating the local variables and also assigning them to a temporary variable. Finally, I will return the value of a after the computation. If we open the compiler explorer, you'll see that even though this function looks very different from what you've seen in C++11, everything can be computed at compile time from the compiler. In fact, we can again use static assert in order to verify that our Fibonacci implementation is valid during compilation. In C++17, as you've seen in the previous sections, lambdas can finally be Constexpr as well. If a lambda returns a constant expression, it will be implicitly Constexpr. Otherwise, the user can place the Constexpr keyword between the parameter list and the body of the lambda in order to force it to be Constexpr. If the user specifies the Constexpr keyword and the body of the lambda is not actually a constant expression, then you will get a compile time error. In this case, using a stdsyn inside the lambda is obviously not something that can be done on compile time, so marking it as Constexpr will prevent the program from compiling. In C++17, we also have a very new important feature, compile time branching. This feature is called Constexpr if, and the syntax looks as follows. It's the keyword if followed by the keyword Constexpr, and in round parentheses, any constant expression which evaluates to a boolean that you can branch on. In this case, this function foo is a template that takes an argument x, and we will execute this block of code only if t is equal to a std string. Otherwise, we will execute the other code block. std is same v is a utility that's in the type traits header, which will return true as a constant expression if the first type is equal to the second type. Let's look more closely at this if Constexpr statement. Firstly, the condition that you provide in the round parentheses must be a constant expression. If the condition is not a constant expression, the program will fail to compile. Both branches, so the true branch and the false branch, must be parsable. This means that they need to contain valid C++ in terms of syntax. But only the taken branch will be instantiated. This means that in the non-instantiated branch, code which is invalid for the current t in this example is allowed. This will be clearer with an example. Imagine this other implementation of foo that takes a const ref and returns an int. Again, we'll check if t is equal to a std string. Firstly, we'll use the regular old if statement. In the true branch, we will return x.length. In the else branch, we'll return x. Now, if we attempt to invoke foo with an std string instance, we will first check the condition, which is true, and we will enter this branch over here and return the length of the string. So far, so good. But when foo is instantiated, the else statement will be instantiated as well, and it will attempt to return x, which is a string, which will cause a compile time error because the function foo returns an int. If we try to invoke foo with an int instead, what will happen is that this check will return false, so we will not enter this branch. We will enter the else branch and return the int, which is okay as the return type of the function is int, but the entire function will be instantiated, including this x.length access, which is obviously not valid for the type int. The problem here is that even though this std_same_v check is a constant expression, the if statement doesn't support arbitrarily discarding a branch depending on the result of the check. Both branches will be unconditionally instantiated and need to be valid for the type t. Let's now take a look at the same function, but with an if Constexpr instead of a regular if. In this case, if we invoke foo with an std string instance, this check will return true, so we will only instantiate the true branch, which attempts to return x.length. This is valid for std string. Note that the else branch will not be instantiated, allowing the function to properly compile. On the other hand, if we call foo an int, what will happen is that this check will return false, so we will only instantiate the else branch, which return x, that is a valid int, matching the signature of the function. Again, the true branch in this case will not be instantiated, so x.length doesn't need to be valid for int. That's it for C++ 17. But what does the future hold for constant expressions? There are proposals being discussed in the C++ standard committee that would allow dynamic memory allocation in Constexpr functions. Something like a Constexpr allocator was proposed to allow usage of the standard library containers in Constexpr functions. The idea is that Constexpr functions might become as powerful as any other function sometime in the future. This would allow you to use data structures such as std map, std string, or std vector as part of the body of the Constexpr function. We have seen an overview of what Constexpr can do in 11, 14, and 17. But why would you want to use Constexpr? The idea is that Constexpr functions allow us to produce constant expressions. Remember that if they're invoked with runtime arguments, they will not produce constant expressions. Constant expressions can be used for compile time, data structures, and algorithms. Performing computations at compile time is faster and safer than doing them at runtime. There are some reasons for that, but the main ones are compile time errors will be produced instead of runtime errors. This allows you to catch behavior that's incorrect during the compilation progress and not when your program is deployed. And code will not be generated or executed at runtime. The compiler will have a chance to compute the results of your functions at compile time and possibly aggressively inline those results in order to produce a faster and smaller binary. Here's another example of a useful function in C++ 14, factorial. In this case, I'm using a result local variable here that starts from 1, and then I'm going to loop from 1 to the provided integer n, and for each iteration of the loop, I will multiply the result variable by I, and finally I will return the value. Again, looking at Compiler Explorer will prove that this function is correct and executed at compile time. Using factorial to initialize a Constexpr int variable will force compile time evaluation of the function. We can then use static assert in order to verify the results. If we don't use Constexpr when initializing a variable from factorial, then we have no guarantee that factorial 4 will be evaluated at compile time. It might, but it might also be evaluated at runtime, even though the arguments are all constant expressions. In fact, using static assert here would result in a compile time error. We need to use the old regular runtime assertion. Finally, if we use something like stdcin, we are forcing factorial to be evaluated at runtime because we have no way of knowing the value of input before we execute the program. Computing functions like factorial at compile time could be really useful when you're dealing with data structures that depend on those results. Imagine that you want to store a set of every possible permutation of some widget class inside an array. You can pre-compute the amount of permutations of the widgets if you know the count at compile time by simply invoking factorial in order to initialize the array size. Since factorial is Constexpr, we can use it instead of hard-coding the result or having to switch array for a runtime data structure. Additionally, the factorial function here can and should be unit tested, especially by using static assertions. If you compare this to having to recalculate and hardcode a value of the factorial of the widget count every time the count changes, then you will see that this is much more safer and maintainable. Let's now take a look at a completely different example, validating strings at compile time. Imagine that we have some piece of software where user IDs are strings that begin with a capital U and a dot. And we want to verify whether a string is a valid user ID at compile time. What we could do is create a Constexpr bool function called isValidUserID that takes any ID of type t, and then returns true if the size of ID is greater or equal than 3, and if the first character is equal to uppercase U and the second character is equal to a dot. Since this is marked as Constexpr, and since this is a template, it will be valid for any type that behaves like a string, both at runtime and compile time. You will notice that we're using stdsize here. This is a new utility introduced in C++17 that homogeneously allows you to retrieve an array or a container size. This will work with stuff like vector, stdstring, but also sys-style arrays. Also, as I previously mentioned, this is a template. This means that it will both work with stdstring and const.jar, allowing you to use it both at runtime and compile time. Again, we can see that using static assert is allowed here, and we can verify that a string beginning with U and a dot is indeed a valid user ID, and a string that doesn't begin with that prefix is not a valid user ID. The exact same function will also work with values that are only known at runtime. If we use stdsin to read a string from the terminal, then we will be able to use assert and call isValidUserID. This will allow us to have a single implementation that works with any type that behaves like a string, both at runtime and compile time. The tunnel is really deep. You can do a lot of crazy stuff with Constexpr. There are libraries such as Prut or Yuki which push the limits of Constexpr by providing complicated algorithms and data structures that can be modified and read at compile time. There's also a very interesting talk and entertaining talk by Bin Dean and Jason Turner called Constexpr All the Things, which shows how to implement a compile-time JSON parser. As you can see from this screenshot, by combining functional programming utilities and new library features such as stdstringView, it is possible to create a Constexpr function that parses part of a JSON object. Later in the talk, they demonstrate how it's possible to use Constexpr in order to completely parse a complete JSON object, to parse a complicated JSON object. Here's a recap for this video. Constexpr functions can evaluate constant expressions. They might be evaluated at compile time if all the provided arguments are constant expressions, or they might be evaluated at runtime otherwise. Constexpr variables must be initialized with a constant expression. If you invoke a Constexpr function to initialize a Constexpr variable, it will be guaranteed to be evaluated at compile time. In C++14, Constexpr functions do not have many limitations as in 11. In 11, they are limited to a single return statement, but in 14, you can use many language features. In 17, we have Constexpr lambdas and compile time branching with if Constexpr. Here are some guidelines that you need to remember. Always define your compile time constant as Constexpr, even if they are simple. This will allow you to use a name for otherwise magic numbers, and also explicitly specify that your intent is not to mutate this constant and that this should be known at compile time. You can use this for numbers, such as this frame rate here, for strings, such as this debug category for some hypothetical log, and even for floats, and initialize that with a constant expression. Even in a local context, Constexpr variables can increase readability. Imagine that you have this read file function which takes a path and then returns a file, and you want to specify the size of a chunk in order to read the file in a buffered manner. If you know your chunk size is compile time, and if you know that it's not going to change, it is very beneficial to mark it as Constexpr even though it's a local variable. This will allow people reading the code to know that this is supposed to be an immutable compile time constant. You should try to mark your functions as Constexpr wherever possible. And also consider using if Constexpr if you have access to C++17 and are implementing some sort of static dispatch. Look for opportunities to write and test Constexpr functions instead of hard-coding pre-calculated computations. This includes constants, array sizes, loop conditions, and validation routines.